Oh, I was muted. Let's give it another minute or two. Okay. All right, we've ticked past 1 more minute. People have had their chance. Um, so yeah, welcome everyone to the 37th uh, Equilibrium Climate Sensitivity and Cloud Feedbacks Virtual Symposium. Um, Today we've got two great rising stars in our field. We've got Nathaniel Tarshish, who's a Hughes Fellow at just started at Harvard, and we've got Arianna, who is a NOAA Climate and Global Change postdoctoral fellow at UC Boulder. Um, so we're going to have them speaking today, and because we've only got two people, you can have a little bit longer time if you want. And yeah, think of questions as the speakers are presenting, and then we'll have a little bit of time afterwards to do some Q&A. You can also type questions into the chat at any time, and we have a backlog of talks if you're interested. And in particular, I want to highlight that we have a new person who's joined the steering committee. This is Matt Luongo, who had just finished his PhD at Scripps and is I think already started at University of Washington as a postdoc, or will do
Very soon.
very soon. All right, well, so welcome, Matt. Yeah, cool. So Nathaniel, you can take it, start sharing and take it away when you're ready.
Okay, can folks see my screen?
Yep.
Great. And is my audio coming through okay?
Mm-hmm.
Okay, terrific. Well, thank you, Andrew, for the opportunity to share this work, which was done in collaboration with Nader Jeevanji and Ines Fung. It goes back to my PhD that recently wrapped up at UC Berkeley. As Andrew mentioned, I just started a postdoc this fall as an environmental fellow at Hughes. And if you want to read more about the work, we've posted a preprint here at tinyurl.com/net-zero-cooling. Okay, so the question I'm going to take on is, how does the temperature change after emissions cease? And you can put this question to models, and you find back a variety of responses. So here I'm showing simulations from a recent intermodel comparison called ZECMIP. ZEC stands for the Zero Emissions Commitment. And that's just the temperature change after cessation. That's what's shown on the y-axis. These models were driven by increasing emissions at roughly 1% per year, and then at a total cumulative emissions of 1,000 gigatons of carbon, emissions were zero. They ceased, and what I'm plotting is the temperature change after cessation. Dashed lines here are EMICS, and the solid lines are CMIP6 models. And what you can see is that particularly over this multi-century timescale, there's a lot of variability from model to model. You have some warming by 3/4 of a degree, others cooling by almost a full degree. Now, as climate scientists, we're probably all too familiar with spaghetti plots like this with a lot of variability. But what is perhaps more interesting is that this variation correlates only weakly with other run-of-the-mill climate metrics. So here again on the y-axis, this is the ZEC at the end of each simulation, so the temperature change from cessation, for each model plotted against different conventional climate metrics. On the left is the transient climate response, ECS, and then TCRE. TCRE is really transient warming divided by your cumulative emissions. So this is teratons of carbon. And you can see that most of the variance goes unexplained here, right? You're only getting R squared at around 0.3. And so ZEC correlates weakly with these metrics, and that really posed a problem for AR6. So in AR6, when they give you a carbon budget, they want to be able to tell you what happens after emissions cease. And because of this uncertainty present in ZECMIP, this large model spread, they had to give a disclaimer that we really only have very low confidence that the carbon budgets they put forward actually stabilizes the climate on these multi-century timescales. So that's the problem we'll take on today. And I'm going to try to make a case for progress in 3 steps. 1, we'll formulate an analytic idealized theory for this post-emissions response. And we'll explain how that theory can shed light into the underlying sources of disagreement that are causing this spread in the models. And then we'll try to constrain using more than ZEC, MIP, more than these particular models, but really other lines of evidence. And say, if we fully constrain our analytic theory, what do we get back? And the upshot will be that I think we can assess with some confidence here that there's actually cooling after net zero. So that's the plan. To start off with, I want to potentially disabuse you of a common misconception. So as climate dynamicists, we often look at runs like this. You have a 1% per year increase in CO2 concentration, which you then hold fixed at a doubling. And temperature-wise, over this transient time scale, say at the time of doubling, you get your transient climate response. And then as the deep ocean warms and no longer serves as an effective heat sink, you warm up to your ECS, which is in most models about a factor of 2 larger than the TCR. And note here, there's a break in the x-axis, so this is really on these multi-century timescales that you realize your ECS. So it's easy to look at a plot like this on the right and think, oh, of course we have warming in the pipeline. ECS is much higher than TCR. But that's a misconception. And that's because this story is missing half of the equation. The other half of the equation is the carbon cycle. So now think about an experiment where you're getting this 1% per year increase in CO2 by actually driving it with emissions, and you're running a carbon cycle. So here you have an Earth system model that you're running. And when the CO2 is at a doubling, you zero those emissions. What happens afterwards? Well, your carbon dioxide falls because there's carbon uptake by the natural sinks. And really, this is no surprise. We know that the land and ocean together have taken up half of our emissions so far, and those processes continue after emissions cease. And a decline here in your carbon dioxide over time is going to result in a decline in forcing. So you're never going to realize equilibrium warming with a forcing at 2x CO2. Instead, many models find a roughly flat temperature response afterwards, as you saw. Okay, so how are you getting this flat temperature response, say in this particular model? Well, it helps to look at the energy budget here. So here I've taken the upper ocean and I'm computing an energy budget for it. And there's 3 main terms. 1, you have the decline in forcing. So you can see it rises during your period of positive emissions. And then after 0 emissions, given the fall in CO2 concentration, you also get a fall in forcing. You shave off about 1.5 watts per meter squared. At the same time, in that 0 emission state right here, you had significant cooling to the deep ocean. And as the deep ocean heats up, you also get this decline here, right? You're mixing down carbon into the ocean and heat. So you have a decline in forcing and a decline in cooling to the deep ocean. And the key point is that these 2 changes roughly compensate for each other, such that the temperature stays approximately flat. And you can see that in this plot, cooling to space is really the feedback term, which is proportional to the surface temperature, which is staying roughly flat. So qualitatively, I'd encourage us to think about this as really a competition between 2 fundamental disequilibria in the Earth system. One is the forcing disequilibrium. In these runs, which are just driven by CO2 so far, it's really telling you about the disequilibrium in the carbon system between the 0 emission state and the final state. And the second is the thermal disequilibrium, which says how out of equilibrium is the temperature of the upper ocean with respect to the deep ocean. That's the qualitative story. And that goes back to papers in the mid-2000s by Damon Matthews and Susan Solomon and Ken Caldera. But how do we make it quantitative? That's the next piece here. And we're going to do something pretty naive. We're going to write down a simple formula for ZEC, where we say if we have some scenario in which we achieve zero emissions, we'll denote that as ZE here for the rest of the talk. What's my temperature at zero emissions? We're just going to rescale TCR by the forcing at zero emissions relative to a forcing at doubling. And likewise, in terms of the final temperature, we're just going to rescale ECS by whatever the final forcing is, which again can be lower than forcing at doubling, given the carbon uptake that's part of the story, to get our final temperature. Now, if you're interested in, does the temperature go up 10%? Does it decline 10% after emissions cease? What you're really after is the fractional ZEC. And if you reminder here that ZEC is just this temperature difference between the final equilibrium and the zero emission state. And what you find is this handy formula right here that has a comparison of two ratios. The numerator here is really that forcing disequilibrium, and the denominator, TCR over ECS, is your thermal disequilibrium, which probes how out of equilibrium the upper ocean is with the deep ocean. Okay, so now we can return to the ZECMIP ensemble and make some sense of it with this formula. We'll revisit these results. First, you can just ask, if I look at, the experimental results here on the x-axis, so here I've just taken whatever temperatures the models realized, and I'm plotting them against our analytic formula. The denominator here, the TCR and ECS, I take from whatever the modeling group reports. And it's actually not clear that they're using a consistent method to get ECS. So I think there's a little bit of definitional uncertainty here, and we'll come back to that. And then the numerator here, I just diagnose the forcings from these runs, and I'm able to compute my formula. And the first thing that maybe stands out is that there's a high degree of consistency between the actual realized fractional ZEC and the one we would anticipate with our formula. We can explain most of the variance. You can see there's a little bit more error here in the warming regime when you have warming after emissions. I think that has to do with the functional form of this expression. If you think of this denominator as x, so this looks like 1 over x, you're getting small x in this regime. And so if you have uncertainty in x, that will blow up like 1 over x squared when it projects onto the result here. So I really think that this spread is basically because we're not certain what the ECS is in these particular models. Anyhow, I think the top line result here is it builds some confidence that we're on the right track. You can also take a look at the outliers, and you can ask, say these two models, which bucked the trend and showed warming. Why did they show warming? You actually find out there's different results between the two. For Burn ECS 5K, it has a very small value of TCR relative to ECS, 0.4 compared to the ensemble mean of 0.6. So what this means is you have a relatively strong heat sink when you zero emissions out here. And the decline of that strong heat sink results in more surface warming. And that becomes the dominant effect over the decline in the heating from radiative forcing going down. So that's why you get warming in Burn ECS 5K. For UVic, it's actually the reverse. The ocean heat sink is relatively standard, but it strands a lot of carbon in the atmosphere. So AF here is the final airborne fraction, which most models put at roughly 0.2, so 20% of our emissions are stranded in the atmosphere on this multi-century timescale. But UVic has relatively weak carbon sinks, so it has a higher forcing than these other models in this final state. And that's why you're resolving warming over time in UVic. And you can play the same game with the models that cool most. And in particular, actually, if you try to apply the theory to PG&E, you really get back nonsense. And if you take a closer look, it's because you find out that PG&E is not conserving energy. It's really an integrated assessment model. It's not an EMIC, and it probably shouldn't have been considered in this analysis. Okay, so now we have some insight into what's going on in ZECMIP. But the real advantage of having an analytic formula is we can transcend ZECMIP. We can move beyond it and look at other lines of evidence. We don't just have to deal with these particular models, this ensemble of opportunity that happen to be submitted. We can instead rely on AR6 and really our integrated assessments of these key quantities. So here's the key formula. And as I'm sure folks are well aware of and probably participated in, there was this big community effort in AR6 to constrain TCR and ECS using multiple lines of evidence and to get kind of a Bayesian posterior for our best estimate of these quantities. And so I'm going to rely on those estimates. And now if we zeroed our emissions today, then this forcing up here, FZE, that's just the present day forcing. And so I'll take the AR6 best estimate of that, shown in this bar here. The only ingredient that's really missing and isn't directly assessed in AR6 is the final forcing. On these long time scales, the last man standing is carbon dioxide. There's not really significant forcing from any other species. And so the key question is, how much of our carbon dioxide emissions are still airborne at that time? People don't run ESMs, full complexity models out to this carbon equilibrium usually. So instead we have to do EMIX. That's really the line of evidence. And if you take the ZECMIP models, you find that their final airborne fractions are clustered at around 0.2, so 20% of our emissions in the atmosphere. And that's roughly consistent. If you just do a back of the envelope calculation, you have an ocean at fixed temperature and an atmosphere, and you ask, under basic carbon chemistry, how much of my emissions would I expect to be stranded in the atmosphere? You get a consistent result. Okay, so those are the sources, the lines of evidence that we're now going to use to try to do a better job at constraining ZEC. If you feed these distributions into the formula, here's what you get. You find the pretty robust signal that there's actually cooling after net zero. You can reject the warming tail here at roughly 90% confidence, and your central estimate of the cooling is around 0.5 degree Kelvin. So, I mean, that's a manifestly different picture than if you just use the ensemble of opportunity that was ZECMIP. But in some sense, it doesn't get to the most relevant question, which is we're not going to stop emitting today, right? Or tomorrow, or probably anytime soon. And so is this cooling after zero emissions, is that relevant to more realistic scenarios where you do achieve net zero sometime in the 21st century? So in particular, in the SSPs, do we expect that after they hit net zero, you'll find cooling? And to evaluate that, I'm going to take a carbon budgeting approach. And what I mean by that is if you look at the AR6 report and you say, I have a particular temperature limit in mind, say 2 degrees. What are the cumulative emissions of CO2 that are compatible with that 2 degree limit? AR6 will tell you, well, if you want the temperature to peak at around 2 degrees, there's this roughly linear relation between the temperature limit and your cumulative emissions, such that you'd expect about 1,000 gigatons of carbon to be compatible with a 2 degree limit. We could talk about in the Q&A if folks are interested why this is linear. But anyhow, that's what AR6 will tell you. I'm going to put a different line down. I'm going to put the equilibrium carbon budget. So here, my final temperature is just a simple function of my airborne fraction and my ECS. C emit is just the x-axis here, what my cumulative emissions are, and C pre is just the pre-industrial atmospheric carbon. So the point is that if I take my best estimate of ECS from AR6 and of my final airborne fraction from these EMIC models, here's what I get back. This is the 5 to 95% credible interval. And the first thing to notice is that the central estimates always have the peak temperature above the equilibrium temperature. So that means that if you, say, emit 1,500 gigatons of carbon, you'll peak at 3 degrees, but then over time, you'll cool by about 1 degree, down to something like 2 Kelvin. So that cooling of 1 degree is really ZEC here. It's the same quantity we've been talking about, and the fact that these two lines are always offset in this manner is telling you that ZEC is always negative. Now you might wonder, okay, if I take into account uncertainty here, what about this overlap region? Does the sign of ZEC change in this overlap? Well, these uncertainties are strongly covariant. So the dominant source of uncertainty in the gray cone is ECS, which covaries with the dominant source of uncertainty in the red cone, which is TCR. So if you're at the top of this cone, you're very likely to be at the top of this cone as well. So even in this gray area, ZEC is likely positive. So excuse me, negative. Okay, so those are some lines of evidence. I'm going to try to add one more, and that's to take an ensemble of simple climate models. This is the FAIR climate model that was tuned to reproduce the central estimates and key uncertainties as part of AR6. So it replicates those AR6 integrated assessments.
2 minutes.
Okay, great. I'm almost at the end here. And the big picture here is that if you take these models, you drive them with the different SSPs. These are the mitigation scenarios. So these circles here are roughly when you hit net zero, you have a peak temperature. And you say, okay, if I'm going to go out on this multi-century timescale, what happens? You find that they all robustly show cooling at this 30 to 40% rate. And so if you take those equilibrium results and the peak results, you drop them down here, you find something that's consistent with the carbon budget we've devised. Okay, so my hope is that, in AR6, what we could say about the multi-century response was really clouded by this ensemble of opportunity. And that by putting together this analytic theory and then constraining it with all of our lines of evidence, we find a more robust result that reaching net zero not only stabilizes the temperature, but actually yields some net cooling over the long run. In the last minute here, I'm just going to do an advertisement for some related work about historical warming. So not future warming, but our past warming and what activities drove it. So if you had asked me that about a year ago, I would have said burning fossil fuels. After all, they're the dominant emitters of greenhouse gases. But the wrinkle, as folks know, is that they also emit most of our sulfur. Sulfur drives the aerosol response. And if you take our best estimates of aerosol cooling in AR6, and you say, all right, if I just emit fossil fuels, so here I'm driving that same FAIR ensemble. If I just emit fossil fuels, what's my radiative forcing over time? You find that it's negative for most of the 20th century. And it's really only in the early 80s that transitions to positive. Now, as our sulfate emissions have gone down, and more importantly, as our carbon dioxide has just accumulated in the atmosphere, the warming due to fossil fuels has risen precipitously. But it's only this decade that it's expected to take over roughly the 50% share from other activities which have been warming us all along and are really what drove warming in the 20th century. So sorry that that's so brief. I thought I'd have maybe a minute or two, but I guess I was long-winded there. But if you want to find out more information, we have our preprint posted at tinyurl.com/half-warming-fossil. Okay. Thanks for your time, everyone, and I look forward to fielding some questions.
Great talk, Nathaniel. Looks like we have a question in the chat from Paolo. On what time horizon did you calculate the ZEC? Also, have you thought about how time-dependent climate feedbacks, for example, through pattern effects, might contribute to the ZEC?
Great, thanks for the question. We're looking at the long-term ZEC. So the timeline that we've been evaluating is multiple centuries. So we take the end of the simulations, which is about 1,000 years roughly. So that's the timeline we're looking at. The pattern effect is in our estimate, right? Because if you take TCR knows about a different pattern than ECS. And we're taking the transient warming and scaling it with the pattern that's in TCR, and the equilibrium warming we're scaling with ECS. So the pattern effect is folded into that.
Great. Anyone feel free to raise your hand with a question or write in the chat. One question that I had, Nathaniel, was did you find in the ZECMIP ensemble if there was any like systematic driver of the spread? Like, was it mostly the emix or anything like some model with a more active or complex carbon cycle, whatever?
Yeah, there seems to be commensurate amounts of spread between the EMIX and the CMIP6 models. It's hard because the CMIP6 models didn't run out this far. But you can even just see from this plot that you have a solid line here, CMIP6. So you have at the extreme, the hottest models on the century time scale come both from EMIX and CMIP6, and also on the cooling extreme, the solid line is a CMIP6 model, this is EMIX. So I don't have a good answer there. I think it's fairly similar across EMIX and CMIP6 models, but the key piece is that there's uncertainty in the thermal disequilibrium, TCR and ECS and what their ratio is, and there's just uncertainty in the carbon cycle, and that's really an independent degree of uncertainty. And so both things, if you do a general decomposition, how much of our uncertainty is due to each degree, it's roughly 50-50. So the carbon cycle is just as important here as the ocean heat uptake.
I think you unmuted me, so I assume that I'm next. Thanks for a great talk. That's really interesting. And I also enjoyed looking at your preprint. I'm wondering, you just said the carbon cycle certainty is about half, and I'm thinking about what more information do we need to generate from fully coupled carbon cycle complex models, so these Earth system models, in order to better constrain that carbon cycle uncertainty, maybe not constrain, but quantify at least. Yes, sort of what's missing from the Earth system model simulation side?
Yeah, that's a great question. So I've been wondering the same thing. I can't directly answer it because nobody bothers running out their full complexity ESMs that long. So I don't know what the ESM answer is. I can show you what the EMIC answer is, and you see that there's uncertainty in land uptake that's roughly the same order of magnitude as the uncertainty in ocean uptake, and they're anti-correlated with each other. So if you look at the model that takes up the least carbon in the ocean, it takes up the most in the atmosphere. So an intuitive response would just be, land is always kind of the boogeyman of carbon uptake, and we need to do better at land. But the models are adjusting for that by compensating with ocean uptake. So I don't have a clean answer for you there, but I would just encourage people to run their models out this long. And generally, as a field, for people to think about the equilibrium carbon state, not just the transient carbon state. As I mentioned, the equilibrium carbon state isn't even assessed in AR6. It's kind of a hole in our carbon picture. Yeah, that's all I have to say on that. I want to know the answer too.
Great. And we have one last question from Tony Broccoli. In the historical slide, what is causing the fluctuations in fossil fuel forcing from the 1920s through the 1960s?
Cool. So if you look at the fossil fuels that's shown here in this panel, and I've just decomposed it into the long-lived forcing from fossil fuels, which is just dominantly CO2, and the short-lived. In this period of time, it's aerosols are really the strong negative short-lived forcing. And so, aerosols only care about what you emitted in the past 2 weeks, roughly. So if we're burning coal at variable rates, then you have short-term fluctuations in your aerosol forcing. And that's what's putting the wiggles in this plot.
Great. And there's another couple of questions in the chat, but maybe we can move on, Andrew.
Yeah,
okay.
Sounds good.
Thanks, everyone.
Yeah, thanks, Nathaniel. Yeah, Ari, if you want to share.
Awesome.
Great. And yeah, thanks, Ari. Take it away.
Thank you. Yeah, I'm really excited to be here. Thank you for the invitation. So I'm really interested in thinking about what drives precipitation change. So this specific talk is going to be thinking about exploring drivers of modeled Western North American precipitation change. And Andrew assured me that this group has evolved to encompass some climate dynamics. So hopefully you'll be interested in this. And so this is work I've been doing as a NOAA Climate and Global Change postdoctoral fellow hosted by Jen Kay at Ceres and CU Boulder, along with my collaborators at NCAR. Okay, so I want to start with kind of the challenges of quantifying drivers of precipitation change as a reminder for the folks in the audience. So while there's high confidence that anthropogenic forcing has contributed to mean multi-decadal precipitation changes across several regions, including but not limited to Western Africa and Southeastern South America. Southeastern South America is primarily where my PhD research was concerned with. It's really challenging to robustly assess the magnitude of relative contributions to greenhouse gas forcing, including stratospheric ozone depletion, especially in the Southern Hemisphere, and the different species of aerosols because of uncertainties in the large role of internal variability on precipitation change. Our observations of precipitation are not the things that we have the most confidence in. Many records are really short as well. Models are amazing tools, but there's lots of uncertainties still in precipitation in models for a variety of reasons. And then our forcings, kind of how the forcings are represented in the models, and then the kind of response to those forcing. All of these things make it really challenging to robustly assess the magnitude of these relative contributions of greenhouse gas forcing. And so that's kind of what I'm really interested in attacking. And so this is just an example from the IPCC on some regional climate change attribution in southwestern North America. So this figure is really cool and shows on the top observations from 4 different observational products for the annual mean precipitation trend over North America from 1983 to 2014. And then, so we can see that there's drying predominantly occurring over the Southwest US. It's kind of the strongest signal across all of the observational data sets. And then the bottom 2 rows are showing 100 member ensembles, either fully coupled from MPI or an atmosphere only model forced with historical observed SSTs. And so I think what's really cool to compare these two is that in the mean precipitation trend in the fully coupled model, there's a really weak drying signal over the American Southwest, whereas when you have the forced historical SST run, you get more of that drying signal occurring that we see in the observations. The driest run also has a greater negative trend in the atmosphere only run compared to the fully coupled. And then you see in the wettest trend in the fully coupled simulation is much wetter compared to the atmosphere only run. And so they conclude that there's high confidence. This is IPCC wording, right? So it means medium agreement based on the robust evidence. So there's high confidence that over half of the anomalous circulation that caused the precipitation decline was driven by teleconnections that stem from tropical Pacific SST anomalies and the Pacific decadal variability, whereas we know that around half of the warming post-1980 is from anthropogenic forcing. So my kind of driving research question is, can we better understand the role of internal variability on precipitation change by quantifying the relative contributions of dynamic versus thermodynamic change in one large ensemble? This one is CESM2 that I'm focusing on. And so kind of thinking about these 2 mechanisms of thermodynamic versus dynamic contribution changes, these are our kind of first order understanding of how precipitation will change under global warming. So by thermodynamic, we're talking about the changes that follow Clausius-Clapeyron, right? Suggesting that a warmer atmosphere can hold more water vapor and gives us the wet get wetter, dry get drier paradigm versus the dynamic contribution, which by this we're thinking about the results that the shifts that result from changes in atmospheric circulation, which can affect then the horizontal and vertical transports of water vapor. And modeling studies have shown that as increased As greenhouse gases continue to increase, this will lead to things like an expansion of the Hadley cell and the subtropical dry zones and poleward shifts in storm tracks. Okay, so my approach is started off by following the methods of Emery and Brown from 2005, who specifically asked to what degree can we attribute atmospheric moisture increase to the changes in mean and extreme precipitation. So I will just be focusing on changes in mean precipitation. And with the availability of a large ensemble, we are now asking, is the forced precipitation response a result of the thermodynamic contribution? And then does the dynamic contribution come from internal variability? The data we're using is the CESM2 large ensemble, looking at daily timescales for vertical velocity at 500 hectopascals, daily precipitation, considering the mid-latitudes broadly from 20 to 70 degrees, comparing two periods, a historical period from 1981 to 2000, and then a future period from 2081 to 2100. This is a fully coupled ocean and atmosphere, land, sea ice, biogeochemistry model, and we're just using, so the large ensemble has 100 members. We're using the 50 members that use the CMIP6 forcing, so not looking at the ones that have the smooth biomass burning forcing, or aerosols, but initial results suggest that the results are quite similar, whether or not you include all 100 models members or just 50. And for the future CESM large ensemble follows the SSP pathway 3-70. And this is just the cartoon that I like to include to see what the climate model looks like. Right, so we have the horizontal, vertical grid, and the equations are solved at all different grids, but I don't think I have to explain that to this group. Okay, so diving into the calculations. So how do we calculate the dynamic versus thermodynamic contributions? So the first step is to obtain a PDF or probability distribution function for vertical velocity for the historical and future period. That'll look like something like this. So this is just an example for the Northern Hemisphere mid-latitude. So on the x-axis, we have the daily vertical velocity, and the y-axis is the relative frequency. So we see that the vertical velocity values are centered around 0 with tails in both directions. So in this case, positive means ascent, and then negative means descent. And so now once we have the PDF, we composite daily precipitation for each omega bin for both periods. And that will look something like this, where again, we have vertical velocity on the x-axis, and now daily precipitation is on the y-axis. So in regions of ascent, that's where we get our precipitation, and regions of descent, there's little to no precipitation. So just including this as an example to show that this methodology works pretty well. And so now the dynamic change is going to be the change in mean precipitation due to the change in the distribution of vertical velocity. So simplified, it looks like just the difference between the two PDFs of the vertical velocity multiplied by that historical precipitation composite into the vertical velocity. And then the thermodynamic change is the change in the expected precipitation for a given vertical velocity. So now we're thinking about how the precipitation composite changed between the historical and future period, and then considering the historical kind of circulation based on that PDF of vertical velocity. So we can find these distributions and calculate the thermodynamic change and dynamic change at each grid point to get maps that look like this on the right-hand side. So these are the results, some of the results from Emery and Brown, just showing the total change on the top, the dynamic change in the middle, and the thermodynamic change on the bottom. Their results were for the annual period. I didn't have time to do a direct comparison to show that for the CESM, these results are quite similar, but hopefully you'll believe me and I'll just dive into the new results. But basically going back to thinking about their method, what are we doing differently? So this paper came out almost 20 years ago. They were considering just 6 different models, or they were considering 6 different models, and we're considering 1. And then of those 6 models, they were looking at 1 run from each of them. So just 6 simulations, and we're considering 50 runs from one model. So we can better quantify the force response, right? And think about better quantify the internal variability without thinking about model differences. They are looking at just annual precipitation. And here for now, I'm focusing on austral winter or DJF. So back to the question. My main question is, can we better understand the role of internal variability on precipitation change by quantifying the relative contributions of dynamic versus thermodynamic change in the CESM2 large ensemble? And our hypotheses are that the forced precipitation response will be largely driven by the thermodynamic contribution, and that the dynamic contribution to precipitation change will be a manifestation of internal variability. These hypotheses are in part informed by this really cool GRL paper by Guo et al. From 2019, where they showed that ensemble mean precipitation trends in CMIP5 and CESM1 large ensemble are in good agreement with the thermodynamic component of precipitation change when considering the extended Northern Hemisphere winter season from 1921 to 2015. So they use this cool dynamical adjustment technique to tease apart the dynamic versus residual or thermodynamic contributions to the observed precipitation trend over this period. And then they show that the residual or thermodynamic contribution to precipitation or to this precipitation trend is largely captured by the ensemble mean from both CMIP5 and the CESM1 large ensemble. So basically what models are able to simulate as far as the ensemble mean or force response is largely capturing that thermodynamic component. And so we're missing out on the dynamic contribution to trends, and this feeds into questions around biases in models being able to simulate trends, which is ultimately what my PhD was motivated by understanding. So tackling this dynamic versus thermodynamic offers another way to kind of dive into and better understand what causes potentially these biases in models. Okay, so after a long-winded preamble, we'll dive into some results. So this is just looking at the Northern Hemisphere austral winter precipitation changes. This is the total precipitation change from 20 to 70 north. We can see there's some increase in precipitation largely over land, some drying over the Mediterranean regions. There's also some drying off the coast of Greenland and kind of the warming hole region, decrease in rainfall kind of poleward of the, or excuse me, equatorward of the storm tracks, and an increase poleward of the storm tracks. Now we can look at the thermodynamic contribution. So at first glance, it really is largely capturing that total precipitation change over land. We're getting some contribution over the Pacific storm track region, and then it's largely capturing most of the Atlantic Mediterranean changes that we see in the total change. And then we can look at the dynamic change, and except for this kind of decrease through the Pacific storm track region, it's really quite muted. The changes over land from dynamics are really quite muted compared to the thermodynamic contribution and the total contribution. And the point I will make is that this is because when we average over these sometimes opposing signs, we'll end up with little to no forced response when we look at the mean like this. Now I'm just showing the same results, but as percent per Kelvin, so just scaled by the global mean temperature change. And you can see the wetting over land stands out really clearly in the total and thermodynamic contributions. And again, we still have very weak contributions when we look at the total response from the dynamics. And this next row that I'm showing is just the standard deviation across the total precipitation change for each ensemble member, across the ensemble. And what we can see is that the variability of changes is in the total precipitation change is really stemming from that dynamic change. And it's really cool to see how large that variability is across the Pacific, especially the Northeast Pacific, and onto the land over the North American West Coast. This is a figure just now zooming in to the North American West Coast, also showing the historical climatology just for reference. But we can see as when we zoom in here, we're getting this wetting over the Pacific Northwest that gives way to drying over kind of northwestern Mexico from the total change in CESM. This is largely captured by the thermodynamics, and there's little to no change when we look at this mean dynamic contribution. And again, you can see that this stands out, or the variability stands out when we look at the standard deviation. Okay, now I want to go beyond the ensemble mean forced response. I think hopefully I've proved to you that our first kind of question or hypothesis that the thermodynamic contribution largely captures the forced response holds true, even just looking at this figure. And so now I wanted to, it took me a while to figure out the best way to dive in and look at what the different dynamic pathways are. And I decided to use a self-organizing map algorithm to do that. So here I'm just showing the results from this 9-node self-organizing map of the different kind of pathways of total precipitation change across this swath from 30 to 50 north over the kind of American West Coast. The percents on the top just show how the percentage of the 50 ensemble members that fall into these respective patterns. I don't have too much time to go into detail across all of them, but what I just wanted to highlight is that this pattern A is the most increased, the most intense wetting. So we have this centralized wetting or localized wetting over Northern California that gives way to some drying, but not much drying at all. Whereas this kind of opposite case where California could potentially experience some wetting across the whole of California by the end of the 21st century. And then now what I'm showing here is the thermodynamic contribution clustered over the ensemble members identified by the SOM algorithm. And what we see is that overall these patterns across the thermodynamic contribution are quite consistent. So even in the wettest case versus this driest case, there's some difference in kind of the extent of which that transition from dry to wet occurs. But overall, kind of that Pacific Northwest wetting is really consistent. And the consistency overall is quite large, which speaks to that kind of the fact that we see that same forced signal across the mean thermodynamic contribution. And then when we look at now the dynamic contribution clustered over the SOM identified members, we see that there's much less variability, right? So the dynamic contributions are really varying across these different pathways of precipitation change, where in the wettest case, the dynamics are contributing to wetting, whereas in the wet case, the dynamics are actually contributing to drying kind of along the entire North American West Coast. And then now, I want to show that the dynamic contribution is related to the internal variability. So this is still the dynamic contribution on the left. And now the right-hand side is showing the total precipitation change, but with the ensemble mean removed. So we can see that the internal variability in the case where California is very wet, the internal variability is lending itself to be wet and looks quite similar to that dynamic contribution, and the same for when we had the dry case, where that thank you, where that internal variability is definitely lending itself towards a precipitation decline. Okay, and so where is what is driving the variability in the dynamic contribution? This is just one way to look at it. This is the projected change in the sea level pressure. And so I'll just highlight quickly that in the cases where California is very wet by the end of the 21st century, we see kind of a contraction of the North Pacific subtropical high, and we get some troughing off of the West Coast. Meanwhile, in the case that California is very dry at the end of the century, we have an expansion of that subtropical high. So the key takeaways is that the total forced precipitation increase along there's a precipitation increase along much of the North American West Coast in the total forced precipitation maps. This is largely captured by and coming from the thermodynamic component, and then the mean dynamic contribution is muted because it largely represents internal variability of the climate system. So better understanding and quantifying and identifying what drives these plausible pathways is crucial to better constraining our future projections. And this is one moment of a really shameless plug. I will be joining the faculty at Dartmouth College in the Department of Geography next summer. So I'm recruiting graduate students and postdocs who are interested in thinking about the different ways that anthropogenic forcing impact hydroclimate versus natural variability and the messy business of untangling these forcings. With that, thank you so much.
Great. Thanks for a really interesting talk. If anyone has questions, feel free to raise your hand and we'll call on you or put a question in the chat. Second. I just had a brief question. When you were doing the decomposition, were you solving for the thermodynamic bit and then like the nonlinear term was with the dynamic bit as a residual, or?
I was calculating the dynamic term and the thermodynamic term, and then
Okay.
also the residual term, but I didn't include it because the contribution is pretty small.
Okay, cool.
Yeah.
Other questions for Ari?
I take convener convener privilege and ask one, but the what is it? I kind of get confused by this like dynamic thermodynamic thing. And I feel like the thermodynamic one is actually kind of sometimes more difficult to understand than the dynamic one. Maybe like if you think about like spread across ensemble members, like so when you showed all of like the internal variability like for the thermodynamic component, like how do I think about that? Like all the models, all the ensemble members are still warming, kind of like. So I think it's like a better way to formulate my question is a spread like internal variability. I understand how that could impact on the dynamics because the circulation just changes differently. But like, what in internal variability is like causing thermodynamic component to change?
Yeah, that's a good question, and I don't think I have a good answer. And I've kind of been stumped by that too, because I think, yeah, like here in this, we're seeing like the Pacific Northwest, like it's pretty clear that the thermodynamic will contribute to that region getting wetter, but what is kind of driving, or yeah, what's the role of or like what's contributing to this kind of increase, yeah, the northerly movement of that drying. And that's not something, so right now I haven't thought about that as much because I've been way more interested in the dynamic piece, but the thermodynamic piece is definitely worth looking at. And it would be cool to see, like, this is just part of this has been kind of thinking through and building up these different frameworks to think about these in a large ensemble. So it would be cool to look at this in other large ensembles that exist and see how different or similar the thermodynamic contributions are across all of the ensemble members.
Is this maybe where like soil moist? I don't know anything about land, but is this where soil moisture changes be felt through thermodynamics? Maybe is that where that lies?
Yeah, that's I don't think about the land as much as I should, but I think that would be a reasonable way to think about that as well. So yeah, is vegetation drying more in these ensemble members compared to the other ones? And is that having a feedback of how much moisture the atmosphere can hold?
Thank you.
Hi, it's Deirdre Desjardins, and I was wondering if you've looked at the Lagrangian model work by the Spanish researchers. They run air packets backwards and track where there's anomalous moisture uptake. But it's really interesting because the Western North America is the one of the very few regions in the world where anomalous moisture uptake has not been increasing as atmospheric rivers go across the Pacific Ocean. And I'm wondering if it's related to that dynamic contribution.
That's really interesting. I haven't seen those models. I'd love. What are there? Is there a paper you could point me to?
Yeah, let me. I'm sorry. My brain is like Swiss cheese lately, so I don't remember their exact name. Or I think it's Oruela Pinto, but yeah, there's a whole group, and they've been running this Lagrangian model a lot. I figured out that Spain is sticks out from Europe and is one of the other regions that gets a lot of atmospheric rivers. So, but the Spanish government has been funding a lot of research. So I'll get it to you.
Awesome. But yeah, I think, thinking about the interplay of so what's happening in terms of the atmospheric variability in observations over the historical period versus the future is what I'm trying to get at. And yeah.
The interesting thing too is Dettinger and Kayan, I believe, looked at like the increase in annual maximum precipitation, and over the past few decades, it's increased everywhere except for in the continental US, except for the West Coast. And it's like, what's going on?
Right.
So I'll get you that too, but this might be a key puzzle piece.
Awesome. Thank you.
All right, great. We're coming up against the hour, so we should probably wrap up. But let's thank Nathaniel and Ari again for 2 great talks. And thanks, Ari, for teaching us some climate dynamics. Yeah, great. Okay. Thanks everyone for coming, and yeah, see you next time.
Thank you.
Yeah.